valence bond theory. So moving beyond just sort of like the first row of the periodic table, like, or well, second row of the periodic table. So like carbon, oxygen, nitrogen, and so on. For elements beyond the second row, we find several examples where the central atom in a Lewis structure had greater than 8 electrons in the valence shell. So when n is equal to 3, L can equal 0, 1, 2. So we've seen that when 4 sp3 hybrid orbitals form, a central atom can accommodate only up to 8 electrons in the valence. So that's sp3, because sp3 is 4 orbitals. For each orbital can accommodate 2 electrons, so 4 times 2 is 8, so that would be a maximum of 8. But of course, we saw in their Lewis structures that some atoms could accommodate more than 8 electrons in their valence. So to place more electrons in the valence, we must bring the d orbitals into the mix, or we must also add together in our linear combinations some of these d orbitals. Does anyone remember a prototypical atom which could act as our central atom that could have more than 8 electrons in its valence? Does anyone remember one of those? Like just one. Right, that's one. Yeah. Okay, so the example was given to me was xenon, so that's one. I could also have given me sulfur, could also given me phosphorus. Those are the prototypical ones, I would say. So consider a molecule like PCl5. So phosphorus, a valence electron configuration of a 3s2, 3p3, it's 5 electrons. Each of the 5 electrons forms a single bond with a chlorine atom. We see over here, it's kind of Lewis structure projected in space. So we have the phosphorus, we have these 3 chlorines, which are kind of in a plane, and then we have one pointing to the left and towards us, and one pointing to the left and away from us. So this means that the central atom in the molecule needs 5 bonding orbitals to achieve the trigonal bipyramidal electronic geometry. This cannot happen with sp3 hybridization because there just aren't enough orbitals. So like 3s and 3p, if we mix these together, there's no creation or destruction of orbitals. Like where we hybridize the orbitals, we have to maintain the same number of orbitals. So these 4 valence orbitals of phosphorus become 4 hybrid valence orbitals. But of course, if we have 5 electrons, that means we would fill one of them completely, which means that we'd have a lone pair plus 3 potential electrons that could be shared in bonds. And so that would not give us this PCl5 molecule. So what happens is we can actually add in another orbital. Like basically with hybridization, you can just keep adding orbitals until such times that you've got enough around the central atom to accommodate all the bonds. So the only way to produce 5 half-filled orbitals on phosphorus is by adding a 5th atomic orbital, which means we need to get access to the 3d orbitals. So this is also why, like, for example, carbon and oxygen and stuff like that, they don't form like 5 coordinate sort of 5 electron domain geometries, because the 3d orbital is the first available d orbital, but they have their valence in the 2, the n is equal to 2 level. So it's too hard. Like the energy difference between the 2 n is equal to 2 or 2p orbital and the 3d orbital is just too large. It's not something that can be easily bridged. But for something like phosphorus or sulfur, no problem. I mean, the next orbital up after the p orbital is the d orbital. So here we do some mixing. We mix the 3s, the 3p, and the 3d, and we get this new sp3d hybrid valence bond orbitals. The reason why we have this is because we've taken one s orbital, this one. We have taken 3 p orbitals, these 3, and we've taken one of the d orbitals. Which one that we take at this stage doesn't matter. So we take one of the d orbitals and we form an sp3d hybrid valence bond orbital. So really the names of these orbitals is just a combination of the orbitals that constituted or make up the valence or the hybrid valence orbitals. So in this case, we've taken an s orbital from the 3s. We've taken all of the p orbitals, so that's three p orbitals, and then we've taken one of the d orbitals, so it's just d from the 3, and we still have the 3d, the other ones, of course. That's where our lone pairs could go, for example. Each of these half-filled sp3d orbitals can form a bond with a chlorine atom in PCl5. And so that's 1, 2, 3, 4, 5. So 5 half-filled orbitals give us 5 potential bonds. So here are some of the sort of molecular structures that we'd seen before for 5 electron domain geometries, according to our VSEPR theory. The one on the left is trigonal bipyramidal electron domain geometry or electron pair geometry. And here we also have seesaw molecular geometry, because the molecular geometry only really considers the bonding pairs or the bonding electron domains. In the case of the one on the right, we have ClF3, chlorine trifluoride. We have a T-shaped molecule, so it has 3 bond pairs, 1, 2, 3, 2 lone pairs. The lone pairs don't contribute to the molecular geometry, but they do contribute to the electron domain geometry. And so these are both, examples of sp3d hybrid molecules. And so, like, for example, you could draw out the hybrid orbitals, and you could see how the lone pairs and how the bonding pairs are formed. So in the case over here, we have sp3d hybridized orbitals for chlorine. So the chlorine valence orbitals will be, so there's 1, 2, 3, 4, 5 degenerate sp3d orbitals. We have chlorine is group 7a, if we recall. So we would have 1, 2, 3, 4, 5, 6, 7 electrons in our orbital. In our hybridized orbitals, we've got 1, 2 lone pairs, and then 3 half-filled orbitals, which can be used as bonding pairs. So that gives us our 2 lone pairs, 1, 2, and then our 3 bonding pairs, 1, 2, 3. So like it's one of the ways, like, I mean, it all matches up. It's not just that I'm telling you this is sp3 hybridized, here's the structure. If you actually look at the orbitals, you can tell as well. Like lone pairs have to be paired. They're not shared, so they're not half filled. So there is some basis to all of this. It's not just like here is something. Believe me, there is some evidence for it. Valence bond theory, so expanded valence, and so we can keep doing this. Like ultimately, so long as we have orbitals available, you can keep adding more orbitals. Eventually, it's not necessary, because one of the things that also comes into play is literally just the size of the central atom. Like there's only so many other atoms which can fit around a sphere. Like once you've filled up the surface of the sphere, there's nothing more to fit in there. So generally, like geometries, as far as we're concerned in this class, will end at 6 electron domains. But you can go further. There are examples of going beyond that. So what about molecules with 12 electrons in the valence? In order to achieve an expanded valence that can hold 6 electron pairs, bond pairs, and lone pairs, we need to form 6 new hybrid orbitals. This requires the mixing of an s, 3 p's, and 2 d atomic orbitals. So we're mixing, or we're linearly combining, or we're just adding up the orbitals in some way, combining them. So here, in order to get our sp3d2 hybrid valence bond orbitals, so that will give us 1, 2, 3, 4, 5, 6 electron domains. So anyone remember the name of the electron domain geometry, or even molecular geometry, which has 6 groups, like 6 electron domains? Anyone remember the name for that? If 4 is tetrahedral, 5 is trigonal bipyramidal, what is 6? Anyone remember? All right, yeah. Okay, those that private message me and those that did it in general. Yes, you're all right. Octahedral. Very good. So so we're combining here. We need 6. So we need 6. So we need to combine. We have 4 from the sp3, and then we need 2 d orbitals. That gives us 6. So 1 plus 3 is 4, plus 2 is 6. So then we have 1, 2, 3, 4, 5, 6 orbitals. So we mix the 3s, 3p, and the 2ds to get our 6 hybrid valence orbitals. So for example, sulfur can do this. So sulfur has 6 valence electrons. So it could be 1, 2, 3, 4, 5, 6. And then each one of those half-filled orbitals can form a bond, and you can have sulfur and 6 other things attached to it. And of course, like the other d orbitals don't go away; they still exist. So sulfur. So we mix the 3s, the 3p, and the 2 3ds in order to get 6 new sp3d2 hybrid valence bond orbitals. So each of these half-filled sp3d2 orbitals can form a sigma bond with a fluorine atom, and that's what ultimately happens. So for example, if I draw it out the way that we used to do it before, so 1, 2, 3, 4, 5. So these are the electrons from the fluorine. So that's fluorine. Okay, you get the idea. And basically, this is how it forms the bonds with each of the fluorines. And so we end up with a structure which looks like this. So the hybridization here in SF4. So we have a general, like our normal, this is our normal valence configuration, a 3s2, 3p4. And so that's still the standard for the atom. But it doesn't really give us enough options to explain why sulfur can actually, form up to 6 bonds, why it breaks the octet rule. And so this model, what's not perfect, does work pretty well for explaining these sorts of structures. So each of the 6 electrons forms a single bond with a fluorine atom, forming an octahedral molecular geometry and electron pair geometry or electron domain geometry. So the bonding can be described in terms of sp3d2 hybrid orbitals, because this gives us 6 hybrid orbitals. That would give us 6 half-filled hybrid orbitals, which will allow us to form our 6 bonding pairs. Okay, so this is the list of instructions which I told you about earlier. So predicting hybridization. So the first thing that we do is we start by drawing the Lewis structure and make sure that we check the formal charges to make sure we have the correct Lewis structure. We then use VSEPR theory, the electron group geometry, to obtain the electron group geometry about the central atom. So we look at bonding pair repulsion, we look at lone pair repulsion, and we try to determine like if it's going to be tetrahedral, if it's going to be I don't know, octahedral or trigonal bipyramidal for our electron domain geometries. Then we relate the central atom electron group geometry to the corresponding hybridization. So generally, like we find, like for example, for methane, so CH4, we have carbon, hydrogen, hydrogen. So we have 1, 2, 3, 4 electron domains. So from VSEPR, we find out that we have a tetrahedral structure. So that equals 4 electron domains. So then we orientate those equally around the central atom. So we end up with a need for these 4 electron domains. So in order to get that, we need 4 hybrid orbitals. So we need sp3 hybridization. That's how we get 4 hybrid orbitals. 1 from the s, 3 from the p. 1 plus 3 is 4. Identify and label the orbital overlap in each bond. So we're just looking to see where the orbitals are overlapping, and then label the bonds with sigma and pi bonds. So obviously, like single bonds, sigma bonds are those which are pointing along the internuclear axis. So in the case of if we had this methane molecule, we have a carbon hydrogen bond. This is a sigma bond because the electron density is predominantly in between the 2 nuclei. If we had a carbon-carbon bond, we could have a sigma bond and a pi bond. Something like that. Okay, so we're gonna try and determine, maybe we'll just do the first one. The first one's quite hard. So the central atom hybridization for the following. It's not really that hard, I guess. I give you a couple of minutes to do it on your own. So just look at xenon tetrafluoride, then I'll ask you to give me your answers. So I'll give you a minute or two to indicate the central atom hybridization for the following. I guess that's okay. No, let's not do that one. Let's do this one. It's easier. Just carbon. So yeah. So for formaldehyde, this one. Give me a couple of minutes. Try and find out the central atom hybridization for the following. So remember that in the first row, the hybridization can only be sp or sp2 or sorry, sp3 hybridized. And n is equal to less than 2. Like I said, maybe a minute or so. Try doing the Lewis structure first. The Lewis structure for that should be fairly straightforward. Oh, wait. Seems like you got it. For those that didn't get it, I'll go through it. So it is, in fact, you're correct, sp2 hybridized. It's much like the earlier one, whenever we had the glycine with the carbon attached to oxygen. So in this case, we're going to count up the number of valence electrons. So 4 from carbon, hydrogen, there's 2 hydrogens, so that's going to be 2 electrons. Oxygen is group 6, so that's 6 electrons. So we have how many valence electrons? That's 12. Draw it a bit of a skeleton. So just draw it out like this. Carbon is our least electronegative, which isn't hydrogen. So we have 6 bond pairs, so it's -6. That leaves us with 6 electrons. We'll first put them according to our rules on this atom as lone pairs. Then we'll check the valence of all the other atoms. So hydrogen has a duet, so that's good. Hydrogen has a duet, so that's good. Oxygen has 8 electrons, so that's good. Carbon, however, only has 6. So what happens is we form a double bond here, like that. And so we now have 1, 2, 3 electron domains. So that means we need 3 hybrid orbitals, 3 electron domains, 3 hybrid orbitals. We're looking at the idea that we have roughly 120 degrees between each of these. It might be, the actual might be slightly different, but we don't know any additional information. So we say it's 120 degrees. We have trigonal planar structure. Sorry, and then we need 3 hybrid orbitals, so we'll have sp2 hybridization. We also happen to have sigma bond here, sigma bond here. This one, what types of bond do we have here? We have, well, it's a double bond, but not much. But what kind of bonds are it? Like, is it sigma only? Is it sigma and pi? Is it pi only? Okay. Yes, those that also messaged me directly, yes, you're also right. So everyone that answered is correct. Yes, that's correct. So this carbon oxygen bond is both sigma and pi. So a sigma bond is the one that's in between the internuclear axis. That's a sigma bond. And then in the other case, it doesn't point along the internuclear axis, but it can still share electrons along the sort of above and below using the p orbitals. This kind of bonding isn't as strong as sigma bonding because the electrons are not shared as easily. It's still good, it's still perfectly fine, but generally it's weaker and forms the basis of a lot of important sort of organic chemistry. But you'll learn about that in organic chemistry, not here. So how do I determine hybridization? First, I draw the Lewis structure, and then I use VS-EPR to determine electron pair geometry. Then I choose hybrid orbitals that match electron pair geometry. Okay, that's a very good question. So somebody asked me if the names of the sigma and pi bonds are just arbitrary or do they have some sort of reasoning. They do have some sort of reasoning, yes, but I cannot explain it well right now, but I will explain it next time. They do have some sort of reasoning, but I can't really explain it right now. But I will next time. I'm sorry about that, but yeah, they definitely do. Yes, it is. So, okay, I also had a question. Is the concept of pi and sigma bonding included in the long test? It is, yes, it is. But not, yeah, you know, it definitely is. We'll cover up to, actually, what's on the long test, I can tell you now, is only up until sp3 hybridization. But I'll make an announcement about that and send it out so everybody's familiar with it later. Well, after this class, actually, that'll be my priority to send out those announcements. Your long test will cover everything up to the end of sp3 hybridization. So how do I determine hybridization? So draw a Lewis structure, use VS-EPR to determine electron pair geometry and choose hybrid orbitals that match electron pair geometry. So Lewis structure is going to be something similar to what we did before. So if we do it for ammonia, I don't really know why they just put a random ammonia here. I guess that's for me to actually tell you about ammonia's Lewis structure, but We've done ammonia's Lewis structure so many times. Okay, so ammonia N is 5 electrons, 3 hydrogens, so that's going to be 3, gives us 8 electrons total. Put the ammonia, put the hydrogens attached to it. That's 3 bonding pairs. That leaves us with 2 electrons remaining, minus 6, 2 from each bonding pair. It leaves us with 2 electrons, leaves us with a lone pair here and here. All right, so we have our Lewis structure. Our electron domain geometry is going to be 4 electron domains. It's going to be tetrahedral, much like methane, but this time one of them is a lone pair. We still need 4 orbitals to accommodate all of our electrons. So we still need sp3 hybridization, because we need 4 orbitals. 1, 2, 3, 4. 1. So there's 5 valence electrons, right? In nitrogen, it's group 5a. That's 4, 5 electrons. So there's our lone pair. And here are our 3 half-filled orbitals, which can be used for bonding, which is what happens whenever they bond to hydrogen. Hybrid orbital mixing. So this is the mixing of orbital wave functions. So this results in new wave functions and characteristic geometry. So the wave function is going way back to quantum chemistry, the way of describing the orbitals, looking at the quantum numbers. Ultimately, whenever we mix together these things, we change in order to get them to point in a certain direction, we need to add certain amounts of, like, for example, S character or P character or D character, and that changes their mathematical equation basically, because believe it or not, like shapes like the p orbital and stuff, there are mathematical equations which can describe that shape. As usually in chemistry, we don't get into the mathematical equations and stuff, but physicists and mathematicians and stuff, they can work all that out. But ultimately, the point is that whenever we create these hybrid orbitals, like our sp3 hybrid orbitals, they point in 3 dimensions, right? So like this, something like this. So in order to get them to point in those directions, we have to combine certain amounts of the pz orbital or px orbital or py orbital. We have to add certain amounts of the s orbital. There are mathematical equations which sort of describe all of that. You add 10% of an s orbital plus 15% of a px orbital plus 50% of a py orbital. I don't know exactly, but it basically goes something like that. You add some, the important thing here is just to be aware that, that there is a mathematical way to describe each one of these orbitals based on the orbitals that they come from. Because whenever we talk about an sp3 hybrid orbital, what we really mean is that we're adding an s, and then we're adding a p orbital, and then we're adding a p orbital, and then we're adding a p orbital to form our total sp3 set of orbitals. But this orbital could be this orbital. It could be pointing along this direction. So in order to get it to point in that direction, it needs to have a different sort of characteristic than this one. Because if not, if they have exactly the same characteristics and the same expression in space, they're going to point in the same direction. So they have to be different combinations of the 3-dimensional orbitals, which are the s orbital, the px orbital, the py orbital, and the pz orbital. So that's what this means by new wave function. Just basically means that we have new mathematical equations, we have new shapes in space. If you plot out the graph of the equations, you end up with a 3-dimensional shape and some characteristic geometry. So multiple bonds are a combination of a sigma bond. The sigma bond is the one that's between the internuclear axis. So this is a sigma bond for a carbon-carbon bond. And then a pi bond, it is somewhere between, so we have the sigma bond, and then above and below the plane, or even in front and behind, we have these pi orbitals. That was kind of the start of chapter 9 when we really looked in detail at sigma and pi orbitals, or pi bonds, sorry. The reason why they're called the way that they're called, I'll have to, I know roughly, but I don't want to say something and then it turn out to not be correct or something. So the structure of ethane C2H6, draw the Lewis structure. Okay, so we have 2 carbons, so 2 carbons, so that's 8 electrons. We have 6 hydrogens, so that's 6 electrons, so that's 14 total. We have carbon, carbon, hydrogen, 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 hydrogen. So how many bond pairs do we have here? Can someone help me, please? How many bond pairs do we have? Yep, thank you very much. We have 7. 7 times 2 is 14, so that means we have 0 electrons to add as lone pairs. So actually, we already have our Lewis structure. All right. Can anyone tell me what the hybridization of either one of these carbons might be? They actually have the same hybridization. So this one, what kind of hybridization scheme do we have here? Okay, yes, we do. sp3, very good. Okay, this is good. It's I think maybe starting to become more okay, getting more participation. I don't know if it's maybe later in the morning, so everyone's more awake, or what it is, but I like it. So determine the number of sigma and pi bonds. So I sorry that I wrote it for this part. Number of sigma and pi bonds. So do we have like, okay, so basically every single bond is a sigma bond. So we have 7 sigma bonds. Do we have any pi bonds here? Do we have pi bonds, yes or no? That's right. No is the correct answer. We only ever have pi bonds if we have a double or triple bond, more or less. At least for the, I mean, basically everything in chemistry has some sort of an exception, but for the purposes of this class, there are going to be no pi bonds without a double bond. So there are no double bonds here. They're all single bonds. They're all sigma bonds. There are no pi bonds in this molecule. Carbon has 4 bonds, sp3 hybridized. We're already ahead of the game. Very good. Carbon-carbon bond is the sp3 overlap. So we actually looked at this in space filling models whenever we were going through sp3 hybridization. The idea that 2 of the carbon tetrahedrons came together to overlap and form a bond. So they form a sigma bond in between them here. Carbon-hydrogen bond is okay, sp3s overlap because the hydrogens don't get hybridized. Those are also sigma bonds. So summary is we have 1 carbon-carbon sigma bond and 6 carbon-hydrogen sigma bonds. So we have a total of 7 bonds. Structure of ethylene then, so this is a little bit different. So, or ethene, sometimes you see it called ethene. So Lewis structure again, so maybe I leave some area. There's probably going to be more stuff come here. So carbon, there are 2 of those. That's going to be 8 electrons. Hydrogen, that's going to be 4, so that's going to be 12 electrons. That we add the carbons and carbons together, and the hydrogens. You could say like, how do I know that this is the general structure? Well, chemical intuition. But you could do you could draw out all of the possible structures and then work out formal charges, and then you would come to the conclusion that this is the correct structure. So we have here 5 bond pairs, so that leaves us with 10, or well, leaves us with 2 electrons. So we put 2 of them here. So we have, check then how many electrons each one has. So this carbon has 2, 4, 6, 8, so that's good. But this one only has 6, 2, 4, 6. So this, in fact, becomes a double bond. So we end up with a double bond here. Then we can look at, oh, why did that all come up? How many sigma and pi bonds? So we have, how many sigma bonds do we have here? First. Yes, that's great. We have, in fact, well, somebody like, thank you, Benjamin, that's also good. So we are already with 1, 2, 3, 4, 5 sigma bonds. No internuclear axis can accommodate more than 1 sigma bond. So we only have 5 sigma bonds. And then the other bond here in the double bond is a pi bond. So all double bonds are made up of 1 sigma bond and 1 pi bond. So to determine the number of sigma and pi bonds, we had 5 and we had 1. Carbon has 3 bonds, so it is sp2 hybridization. Oh, I forgot to ask you about that. 1 carbon-carbon bond is sp2 overlap. So hopefully you can see why it's sp2 hybridization. Yes, the reason why it's sp2 hybridization is because there are 3 electron domains, 1, 2, 3. So that means that the geometry of each carbon is going to be trigonal, planar, like that. So there's 120 degrees between each of the bonding, between each of the electron domains. So that means we have 3 electron domains, which means that we need 3 hybrid orbitals. So sp2 hybridization gives us 1, 2, 3 hybrid orbitals. Okay, so we have 1 carbon-carbon bond is sp2 overlap. We have a sigma bond. Carbon-carbon bond is pi-pi or pp overlap. This is the p bonds or the p orbitals, so like these ones. Basically the one that's left over. So whenever we hybridize sp2, so we start off with 1 s orbital and 3 p orbitals. We then hybridize to form sp2 orbitals. So we end up with 1, 2, 3 sp2 orbitals, but we still have 1 p orbital remaining, like so. So we fill these up. So 1, 2, 3. We need 3 orbitals for our electron domain geometry, and then we have 1 remaining for, well, that we don't need actually, in order to fulfill the bonding. But this half-filled p orbital can be shared with the other half-filled p orbital on the other carbon, like so. So that's carbon, carbon. And so they can share this, like they can form a pi bond using these half-filled p orbitals. So that's this pi bond here. And then the carbon-hydrogen bonds are sp2s overlap because the hydrogen doesn't get hybridized. So the summary here for C2H2, so this is acetylene. So draw the Lewis structure. So again, we have here 2 carbons, so it's going to be 8 electrons because they're in group 4, so they have 4 valence electrons, and for the 2 hydrogens, 2 electrons, gives us a total of 10 electrons. Then we can draw this out like our skeleton here. Okay, we have 3 bonds, so that's -6. So it gives us 4. Then we can put 2 lone pairs on the 2 carbons. we find out that both carbons have only got 6 electrons. So in order to like provide this one with more electrons, we can form another bond here, which is a double bond. So that means that this one now has, maybe if I can erase that. Okay, so this one is shared its lone pair. So this one now has 8 electrons, but this one still only has 6. So those lone pairs are then shared in to form what will become a triple bond. Like so. So the triple bond here is, actually, does anyone remember the definition of what a triple bond is? Like what it's made up of? It's made up of a sigma bond. It's made up of what else? All right, that's right. Very good. With the sigma bond and 2, what do you call this? 2 pi bonds. Okay. So then determine the sigma and pi bonds. Okay. So how many sigma bonds do we have? I always forget what the order is. Okay, so we're saying we got 3. How many pi bonds then do we have? All right, we're saying we got 2. So that seems right. 3 plus 2 gives us 5. We have 5 here. So 1, 2, 3 sigma bonds, 1, 2 pi bonds. I agree with that. The carbons then. So what kind of hybridization do we have on the carbons? Remember, count up the number of electron domains and then see how many hybrid orbitals we need to form. Yep. Everyone's messaged me, everyone's messaged in chat. You're all correct. These are sp hybridized because there are 2 domains. One here and one here. And for this one, one in the middle and one there. So they're both sp hybridized. So that means to form the carbon-carbon sigma bond, we have sp hybridized orbitals overlapping. To form the pi bonds, we have p bonds or p orbitals overlapping. So basically what we have in the case of the carbons is sp orbitals here, which are half filled. And then we have p orbitals, which are also half filled. So that gives us 4 electrons. So it's 1 carbon and then the other carbon has the same sort of electron filling. So then we can, for example, combine these 2 to form 1 pi bond. And then we can combine these 2 to form the other pi bond. And then, for example, these 2 can form the sigma bond between the carbon and carbon. And then these can form the sigma bond with the hydrogens. If I get a different color, it would help. So, oh, purple and red. Basically the same color, or similar anyway. And so that ends up being something like that. So yeah, so carbon-carbon sigma bond is sp2. That's wrong. It's sp-sp. That's not correct. They're sp hybridized. So the there's only 2. That's why they didn't change it from the previous one. Okay. And then suddenly we go to sp3d2. Okay. So additional examples of sp3d2 hybridization. So bromine pentafluoride is one example. So bromine pentafluoride has 5 bond pairs, 1 lone pair. It has square pyramidal structure. So the molecular geometry here is square pyramidal. Here we have on the other side xenon tetrafluoride. Earlier on, I asked which are the prototypical or the most common atoms which display this sort of extended valence, this extended octet, where they go beyond 8 electrons. And so xenon was given to me correctly as one of the potential atoms, as a central atom. So it likes to form these square planar complexes with fluorine, where it has 2 lone pairs and 4 bond pairs. And so it has the molecular geometry, which is square planar. So the conclusion here is that molecules with an octahedral electron pair geometry have sp3 d2 hybrid